uh, to the third talk of this session, which is by Professor Rajan, C.S. Rajan of the Tata Institute of Fundamental Research, Bombay. He's going to talk to us about restrictions of representations. Rajan, over to you.
Okay. So thanks, Raghavan, and thanks, Venkatesh. At the outset, I want to say that uh, this is not a talk meant for experts or not for beginners. I don't know who will gain from this, but let me just continue um, with this. Right, yeah. So, yeah, I'll come much later to why I got interested in this, but that will be towards the end of the talk. Uh, so, uh, so this is, what is the setting? You're looking at an inclusion of two compact connected Lie groups, K containing set K tilde, and the problem is to describe the decomposition of a representation rho tilde of K tilde to that of K. Yeah. So that is what we would like to do that. And since the representations of a compact group are completely reducible, you can assume that rho tilde is irreducible. And I'm just setting up some notation and also talking some things. So then you write, of course, you can write rho tilde restricted to K as a direct sum of irreducible representations. And so K hat denotes a collection of irreducible representations. And the question is, what are these representations rho, and what are these integers, and yeah, how how do they vary as you vary the parameters involved? What are the properties which you get? Um, so I just want to say a bit before going further that while unitary trick says that the representation theory of a connected reductive algebraic group G over C is equivalent to that of a maximal connected compact connected subgroup Kg of G, and similarly, you can also work at the level of Lie algebras. If G is semi-simple and simply connected, its representation theory is equivalent to that of the Lie algebra G. The reason I'm saying, as it will come obvious in the when we go ahead, is that the different viewpoints shed different lights, and some of the things are easy to see in one viewpoint than the other. Uh, of course, it is always a challenge or a thing to prove it in using the other viewpoints or other ways of looking at representation theory. Yeah, and of course, the Lie algebraic version, one can try to generalize it to other contexts, in which case, Cast Moody or other contexts where this compact groups or the algebraic setting is group of algebraic group setting is not available so easily. Okay. Uh, at the level of Lie algebras, you can write G can be written as a sum of simple Lie algebras. An irreducible representation can be written as a tensor product of irreducible representations of the irreducible components of G. Okay, I think this has come slightly out of the way, but a typical example I want to say is when K is the unitary group UN, or the unitary group in n variables. Equivalently, you're looking at the representations of the group GLNC or that of the Lie algebra GLNC of all n cross n complex matrices. So this is always a very good example to hold and keep in mind, and most of the problems are there even in this case. So let Tk be the subgroup of diagonal matrices, and it's isomorphic to S1 power n, the circle group power n, and it's a maximal commutative closed connected subgroup of K. So the elements of Tk act as unitary matrices in any representation, and hence the representation of rho restricted to Tk can be simultaneously diagonalized. And I just want to say that given a non-zero vector V for rho Tk, we have rho T times is lambda T times V with the eigenvalue lambda T. Then this function lambda T is a character of Tk, and these are the eigencharacters or the weights for the representation. Anyway, I'm just saying obvious stuff which is there. And you get a weight space decomposition, rho restricted to the maximal torus T is going to be direct sum of the weights where m lambda p, m lambda rho are the multiplicities of the eigencharacter, or what is called weights, lambda occurring in the decomposition of rho. The question out here is to, of course, describe the multiplicities m lambda rho, by which, of course, there is also a geometry which is involved. I'll just go through this. What are these multiplicities, when do they occur, what are the relationships between them, and things like that. Okay, so that's just another way of looking at this. The study of the representation theory of K is equivalent, in a sense, the dual sense, to the problem of studying its conjugacy classes. And what one is looking at is saying is every element of in UN can be diagonalized, but this diagonal representative of the conjugacy class is not unique and is determined only up to a permutation. All right. And so now you look at NKT be the normalizer of T in K, and WK is a while group, the quotient of the normalizer by the torus T. And the space of conjugacy classes is the same as that of the W orbits of T. So in some sense, what one is looking at is that you have to look at this with the action of W, which occurs in a natural manner. And so the normalizer acts on the collection of weights of rho via the quotient while group. So what happens is one thing which we see immediately is that these weights carry with it an action of the while group W. So this is one part of it. The second part is that you see that the Lie algebra of UN consists of skew emission matrices. So the diagonal entries are purely imaginary. And if you look at if lambda i's are the eigenvalues, then the quadratic form summation lambda I squared is negative definite and is conjugacy invariant. And this gives rise to the killing form, and it extends in an invariant manner to that of the Lie algebra. Okay. Okay. Now, what is the first main example which one has? The real thing is the representation of K on the adjoint representation, that is on the complexification of its Lie algebra, the Lie algebra of the complexified group G. Yeah. So that is the weights which occur in this are called the roots, and the classification of simple Lie algebras is done by other properties satisfied by the roots, the action of the while group, and the invariant form. So anyway, these are all well known. I should not even talk about these things in such an audience, but this is more for myself. So anyway. And key to the study of the classification, the weight space decomposition of an irreducible representation is a study of the action of the root space SL2 connected to any root alpha. And so the SL2 space, which is, so if you have a eigenvector for the x alpha for the root alpha, and then you look at x minus alpha, and then you can look at the commutator element H alpha, and together with this pair X alpha, X minus alpha, and H alpha, they determine an SL2, and the study of the representation theory of the decomposition of V as a sum of its weight spaces. The main tool to study it is the SL2 corresponding to the various roots alpha, right? Okay, so now, of course, the problem with working with the compact group situation is that the X alphas do not lie inside K, the Lie algebra of K, but they lie inside the complexification, the Lie algebra of G, GL, and C. For example, if you are working with this, so it gives. So, for instance, the choice of a Borel, the upper triangular subgroup, and looking at the EIJs or whatever it is, those vectors, they give you the they are the eigenvectors for the action of T, and those X alphas that lie in the Lie algebra of B will be deemed as positive roots. And we also have the partial ordering is defined on the space of weights by defining non-negative integral linear combinations of roots to be positive. Okay, and weight is said to be dominant if lambda of H alpha is greater than or equal to 0. This H alpha, one can think of it also as a co-root alpha check, which is there. And the theorem of the highest weight is that isomorphism classes of irreducible representations are classified by their highest weight. For example, given a representation V of UN, irreducible representation, the action of T on the one-dimensional space of invariance with respect to the strictly upper triangular group NN yields the highest weight vector associated to V. Yeah, I can't immediately see why it should be non-zero, one-dimensional, and this thing, but I suppose there should be a way of seeing it from one of these viewpoints. And this weight is dominant and the unique highest weight with respect to the ordering among the weights that occur in the representation. Maybe, yeah, anyway. And the question for the inclusion T contained inside K is to describe the collection of weights counted with multiplicity, its geometry, etc., in terms of the highest weight. So I just want to state one result. So it can be seen that the collection of weights that occur in the irreducible representation V lambda with highest weight lambda. So you take the translate of lambda with respect to the root lattice with respect to the highest weight lambda, and you intersect it with the convex hull spanned by the W translates of lambda, and this is the support. So all the weights which occur in the restriction of V lambda is just you intersect lambda plus the root lattice, uh, the translate of the root lattice with the lambda, and intersect it with the convex hull of W lambda. And so that's a and so in some sense these are the weights of the form lambda minus summation. So I forgot to put it, alpha and delta of n alpha times alpha, where delta is a base and n alpha are non-negative, which lie in the convex hull with the corner points being given by W lambda for W and W. So in particular, it is convex with respect to the root lattice. I'm sorry, there is a lot of typos in this, but maybe, I hope, yeah. Anyway. Okay, so I just come back so the proof of this for alpha root, this follows from the SL2 theory attached to a root, which is there. For a general alpha, it follows from the induction on the length of alpha when written in terms of the base. So this is, I think, for instance, proved in Bourbaki, chapter 7, part 8 and chapter 7 or whatever it is. But it's also there in Katz's book, this that it's convex with respect to this entire root lattice. Okay. There is also, from the Weil character formula, you can derive the quotient multiplicity formula recursively in terms of the weights. But this is in terms of the partition function. Sorry, you can't see it, which is, wait.
I think it is overflowed on that page.
Yeah, it's overflowed. Okay. Maybe I can zoom. No, it's okay. I don't. Anyway, this people know, but the point is that this partition function, which gives you a number of ways a weight can be written in terms of the non-negative root vectors, the non-negative roots. Anyway, so but this formula does not seem to be of much use, is all that I want to say. Okay, before I go further, I just want to talk about the main topic in some sense, which is what is called the additive eigenvalue problem. I also want to say that there are a couple of references which are excellent. One is Shravan Kumar's article, which was there. It's called the additive eigenvalue problem, 100 pages long. But there is also an article by Briand in seminar Bourbaki, which is also very nice, on the work of Resser, and this, which gives you the general question. Okay, so the problem is that of what is the additive eigenvalue problem? So this is of determining the possible relationships satisfied between the eigenvalues of two Hermitian matrices A, B, and the sum, which is C, which is A plus B. Okay, one condition which you see is that the sum of the traces should be equal. So this problem was considered by Hermann Weyl in 1912, and many people have been contributed to it, and subsequent work by many people. And the general conjectures. So let me, before going to this general conjectures, let me say how the various inequalities which arise. So one inequality which arises is from studying the maximum values of the Hermitian forms. The Hermitian form, AV comma V gives you a Hermitian form on the vector space V. And so you look at the maximum on the sphere of norm 1. And the value is known to be the maximum of the eigenvalues, because the eigenvalues of the Hermitian matrices are real. So you can look at it. So it's the maximum of the eigenvalue. And so this yields, of course, it's a typo there. Nu 1, the maximum of the eigenvalue of A, which is nu 1, the maximum of the eigenvalue of B, which is nu 1, it's not nu plus 1, which is less than or equal to lambda 1, which is the maximum of the eigenvalue of C. Okay. Now I just want to say there are inequalities which are known as the minimax inequalities, which generalizes this maximum thing. So what minimax inequalities say is that the lambda jth eigenvalue is given as the maximum. You take the space of dimension j, and amongst that you look at the minimum of uh, the Hermitian form restricted to it, and then take the maximum as you vary the dimension, or as you vary the space subspace of dimension j. Okay, I think yeah. Okay, so V is a subspace maybe out here of dimension j. So you vary the subspaces of dimension j, and outside in that you take the minimum. This also happens if you work with the complementary dimension and work with the maximum. Okay, so there are minimax inequalities which is there. I just wanted to say that the minimax inequalities, which was considered by Hermann Weyl, it gives you other inequalities relating of the eigenvalues. And the point I want to say is that these inequalities arise from looking at various subspaces, for instance, subspaces of dimension j, and look and intersect it with the complementary, some suitable subspace, and intersect it with the complementary subspace of dimension n minus j. For instance, you can take the subspace generated by lambda 1 to lambda j and intersect it with the one of complementary dimension, so that you will have exactly lambda j occurring in that. And that's where the eigenvalues, this minimax inequality gets attained. And in some sense, this principle is what goes into Kleitschko's work of looking at Schubert varieties and intersections. So in some sense, it's these ideas which gets translated by Kleitschko into Schubert varieties and intersections. Anyway, I'm jumping forward, but let me just. So I just want to recap Horn inequalities. Not that one can make sense of it immediately, but the point is that what I want to say is that the Horn inequalities have an inductive procedure definition to them, and that is one aspect. The second aspect about these inequalities satisfied by the eigenvalues, or they're all linear. Okay, so this is one thing which I want to emphasize. So I just want to flash in front of you the Horn inequalities. So you have, what we like to say is all the inequalities are of the form summation lambda k is less than or equal to summation mu I plus summation mu j, where I, j, k are subsets of 1 to n, all having the same cardinality. Okay, and the collection of such admissible sets of dimension n and cardinality r will be denoted by T and R. And the definition of T and R is done in an inductive manner, and it is done. So we'll write the indices increasingly. For R equal to 1, ijk is admissible if k1 equal to I1 plus j1 minus 1. So these are the inequalities which you get from the minimax things. If you apply the minimax and put R equal to 1, and you work with these indices k1 equal to I1 plus j1 minus 1, you get certain lambda of I plus j minus 1 is less than or equal to mu I plus mu j minus right, mu I plus mu j. That's an inequality which you get from the minimax. Okay, and for R greater than 1, it is defined that ijk belongs to T and R if and only if this condition that summation I plus summation j equal to summation k plus some shifted by p plus 1 choose R, and then for all p less than equal to less than R, you and so subsets u, v, w in TPR, this following inequality should be satisfied for the indices. So these are the admissible sets, and for these admissible sets, the eigenvalues should satisfy the inequality which I stated above, that the summation of the eigenvalues belonging to that subsets should satisfy this inequality.
Sorry, Rajan, what is p plus 1 in the first, if I may ask? If you go back to the previous, what was p before you defined p less than r minus 1? Was it defined earlier also?
P, small p?
Yes.
No, small p is inducted. You say that some element set, admissible set in T and R, if for all p less than equal to less than R, satisfying these conditions, these are the admissible sets. See, R ijk belongs to T and R. These conditions should be satisfied. First of all, for summation I plus summation j equal to summation k plus the equality should be satisfied.
Yes, what is P there? That's exactly.
And for all P less than R.
No, I guess in the first equation.
The subset of the indexing set, right?
In the first equation, P is not specified, is my question.
Which first equation?
For R bigger than 1, blah, blah, blah happens if and only if something equality. But what is the P on the right-hand side of that? Because for the second equation, you mentioned what is P. But for the first equation, it's not.
No, the two sets are related. The two sets are related.
Oh, that should be n plus 1 choose R.
N plus 1.
Oh, n plus 1 choose R. Oh, I see.
Yeah.
And then for all P, the next equation.
Yes.
Okay.
Sorry. Yeah. Thanks. Yeah, it is n plus 1 choose R. I suppose it's correct. Yeah. Okay. Yeah. Thanks for listening. Yeah, good. At least. Okay.
Sure.
So these are the admissible sets which are necessary and sufficient for the existence of emission matrices satisfying A plus B equal to C. The point is that all these inequalities are linear, right? And so it's a convex body, it's a convex polytope, and with linear inequalities. Linear. So it's a convex polytope. So this convex polytope property, it arises from an application of the convexity of the moment map applied to the coadjoint orbit. So this is a result of Hikman, 1982. So there is I should say, it's of course, as usual, there is a lot of work. It's probably the work by Constant, and then Atiyah looked at convexity of the moment map, and many others looked at it. And Hikman applied it to the coadjoint orbit, and so got some results. I'll explain what the thing is. I'm just going to say a bit. I'm not going to say much more because I'm fairly ignorant of many of the things which I'm talking about right now. Okay, so now what happens is, so the coadjoint orbit, starting from the work of Kirillov, is you look at the Lie algebra of K tilde. K tilde is a bigger group. I'm looking at that. And lambda is a weight vector there. And I'm looking at the orbit of K tilde of lambda, inside the K star. See, lambda is an element of the dual space. So I can think of it as an element in the Lie algebra by looking at the derivative. And so I'm thinking of Lie algebra of K, and so it's an element of the dual of the Lie algebra of K. And I look at the K tilde orbit. This is a coadjoint orbit. And point is, it carries a natural symplectic form, which is that you look at, so the xi and the eta are elements of K tilde, so they are, which is there, and they act on the orbit. So when I take the exponential map on xi and eta, so they define vector fields on the orbit. And so what happens is the symplectic form has to be defined on the orbit lambda, on the manifold. And for the vector fields defined by xi and eta, you define it to be just a minus lambda of the Lie bracket of xi and eta, which is there. Okay, so defined by this element. So xi and eta are in this Lie algebra of K tilde. Yeah. And I don't want to get into the definition of the moment map. As I said, I don't really understand many of these things, apart from maybe I could have said what the definition is, but I don't have a feel for it. The moment map for the K tilde action of the coadjoint orbit, it turns out to be the above inclusion of O contained inside K star. The moment map is a map from the manifold M. If a Lie group acts on it, the moment map in a symplectic manner, if a Lie group K or whatever K tilde acts on a manifold M in a symplectic manner, and it's supposed to be Hamiltonian, the action is Hamiltonian, then there is a moment map, and it's a map from the manifold M to the dual of the Lie algebra, which, and that is K star out here, Lie K star, and that is what one is looking at. And that's just a natural inclusion as a moment map. Anyway, and now there are natural projections because I'm asking for K sitting inside K star. I've forgotten one arrow. Yeah, so you look at the dual of the Lie algebra of K, and that restricts, that's a map there is a map to the dual of the Lie algebra of K tilde. There is a restriction map to the dual of the Lie algebra of K, and from the dual of the Lie algebra of K, there is a map to the dual of the TK star of the diagonal torus. And CK is contained inside Lie of TK star is a fundamental domain for the action of W. Okay, so then the theorem of Hikman or whatever, which is probably done in a more simplistic context, in a more general manner by Kirwan and others. The projection of the orbit, so I'm taking the orbit generated by the eigenvalue, the maximum highest weight, the coadjoint orbit, and I project it to the Lie algebra of the subgroup and project it to the diagonal torus, the maximal torus there, and look at the intersection with the fundamental domain, right, for the action of K or the action of the while group. So it is so what it says is a convex polytope. So if I apply this to the K direct sum K sitting inside K direct sum K, I really get the Horn convex polytope in some sense. I know I'm not saying it gets it, but what I'm saying is it says that it's a convex polytope. That what are those specific inequalities which you get from which Horn has said, that requires of course proof, and which is rational if lambda is rational, lambda is so. And assume that the rationality hypothesis, the rational points mu which are in the which are in CK, or those for which there exists a integer n greater than or equal to 1, such that the multiplicity of m of n nu comma n lambda is non-zero. Okay, so nu is a highest weight on K, lambda is a highest weight on K tilde. Okay, oh my god, there is a yeah, sorry, this is the notation is changing quite a bit. It is m of n times mu, n lambda is non-zero. So these are the thing. Anyway, so what it says is that you look at this is what is called the saturation eigencone or whatever it is. So you're looking at all the multiples of n lambda and look at the representation and restrict it to K and look at the weights for which n nu occurs, right? These are the weights which is there, and this is the cone. This is what it is. Okay, the first part, as I said, the convex, that it's convex polytope, it follows from the work of many people. The second part, when you work with the convexity and this coadjoint, the moment map, you can interpret it in terms of Mumford stability, and which automatically says some space of sections are non-vanishing, and by Borel-Weil theorem, you get this. So that's a thing, but let me just specialize to the additive eigenvalue problem. So you define the eigencone gamma E to be the collection of real, or we'll just work with the purely imaginary, n tuple of eigenvalue of elements h1, h2 to hm, which belongs to a fundamental domain on the torus, and which are respectively eigenvalues of skew emission matrices Ki satisfying K1 plus K2 plus Km equal to 0. So this is the space which you want to identify. You look at the space of eigenvalues corresponding to skew emission matrices, which are, of course, I was looking at Hermitian matrices, but if you take a Hermitian matrix, then I times a Hermitian matrix is skew emission and so on. So you can move back and forth between Hermitian and skew emission. So that's not a serious issue. So you look at Hermitian matrices or skew emission such that the sum is 0, and you're looking at their corresponding the diagonal entries or the eigenvalues, and you would like to describe this cone, which is what is happening, right? This is the eigencone which is there, and what happens is you can define the saturation cone. So I could have worked again with K. So you look at the dominant integral weights lambda 1 to lambda m, such that the space of G invariants of the vector space V of n lambda 1 tensor V of n lambda m is non-zero for some n greater than or equal to 1. Okay, so this is a saturation cone, and then the other one is eigencone. Okay, so what the previous theorem specifies, translates out here is that you can take the so the eigencone is sitting inside the Lie of the diagonal algebra T, and via the killing form you can identify T star, and weight lattice sits inside that, the powers of that. So you look at the eigencone, which is phi of gamma E, sorry again, and intersect it with the lambda of m plus. So this m should be, this script m should be E, and then you get gamma of S, the saturation cone. Okay. So this kind of relates the additive eigenvalue problem to the saturation problem. In some sense, what one is saying is that the inequalities satisfying both the conditions are the same inequalities. That's what one is saying, right? So if you solve one of them, you solve the other in some sense. Okay. What Kliatchko did is to relate these conditions to the Schubert calculus. So given a parabolic P, you let WP be the while group of its Levy, and you look at the quotient, the coset space W mod WP. And one knows that in this case that every element for a maximal parabolic subgroup, every element can be as a unique representative, as minimal length representatives for this. And now for W and WP, then the Schubert variety is defined as a closure of the B orbit of W in G mod P, the closure of the set BWP mod P. Yeah, so what is Kliatchko's theorem is that an element is in the saturated cone. The saturated cone is this collection of highest weights, so that some multiple tensor product of the multiples of it has some non-zero invariance. If and only if for every standard maximal subgroup, parabolic subgroup P in G, and you look at a collection of Weil elements in this coset representatives, such that the corresponding Schubert varieties intersect non-trivially in a zero-dimensional variety. So there is an inequality which holds that lambda j, which is the eigenvalues which are corresponding to that, and then you look at Wj inverse, and H alpha is a co-root, which I said, which is unique co-root which is associated to the parabolic subgroup, right? Which is a unique simple root. Okay, I think I think my lectures are neither here nor there, but okay, the conjectures of Horn, what happens is it gets established in an inductive manner. We translate the above inequalities. You know, these inequalities can be stated very specifically for SLN and its maximal parabolics. And then you essentially get the inequalities which you get by Horn when you work it out. And together the proof of the saturation conjecture due to Knudsen and Tau. The saturation conjecture of Knudsen and Tau is that if you look at the sum of the highest weights, if they belong to the root lattice, that's a necessary condition. Then the tensor invariance for some multiple of n is G is non-zero if and only if you can drop the n and work with this. V of lambda 1 tensor, V of lambda and G is non-zero. Yeah, I don't think I'll get more into it, the proof of this. This is okay. So let me say why it was interesting to look at this. Is that what happened? So it's a bit of history. So I was working with Ravinder, and we are looking at some diagrams of tensor product decomposition, and it seemed as if that they're all convex with respect to the root lattice. And the question was whether this convexity property is true. So we are trying to look at that, and then it turned out that did some calculations with Rekha Biswal. It also turned out to be true, and then later on Rekha and Hariharan Narayanan, it was clear that the saturation property and the convexity property implies the following convexity property for the support. It's almost immediate. So suppose alpha is a root and V lambda plus K alpha occur in a tensor product V mu tensor V nu for some K greater than or equal to 0. Then the representations with highest weight V of lambda plus J alpha occurs in V mu tensor V nu for 0 less than or equal to J less than or equal to K. So this is an immediate corollary follows from this. Of course, so it's kind of this convexity property is interesting. It is like what is happening for the restriction to the weights, which is there. Yeah, as I said, it's thanks to discussions with Ravinder, Rekha Biswal, and Hariharan. So just like in the restriction of to maximal torus, so I don't know what one can say. So there one knows what's the alpha chain. At least for alpha is a root, you know that the alpha chain is just through mu is just mu evaluated on the co-root, right? That's the length. So can one say anything about the alpha chain? Is there a possibility of saying anything in the case of tensor product? This is, of course, one can raise other questions, but I'm just raising this. Yeah, the problem, of course, is that we do not have this kind of SL2s attached to root vectors that work so well for restrictions to maximal torus. Just a speculation. I don't know whether one can get this over by going to the universal enveloping algebra or looking at deformations which preserves the tensor product structure, or like looking at current algebras. Of course, I should say anyway. It's not clear how the universal enveloping algebra of direction of to G direction G and its relationship with that of G. I'm sure it should have been studied, but is it possible to get some kind of some SL2 which is sitting inside, which kind of commutes with the diagonal universal enveloping algebra, and which kind of will produce this kind of decompositions or the alpha chains which is there. Yeah, so that would be a nice direct proof, which would be good rather than going through saturation. Okay, so my last slide, the convexity property for support seems to hold whenever the saturation conjecture is valid. It is conjectured by Kopovich that the saturation property holds for other groups too, provided the weights are regular. Yeah, so in which case, I suppose the convexity property should hold for this. For the supports. Question of multiplicities, it was Okunko had looking at, made some conjectures regarding multiplicities, and he had some probabilistic reasonings looking at the unitary group UN as n goes to infinity, and he conjectured that the multiplicity should be log concave, meaning, if I look at the multiplicity of mu in lambda and mu dash in lambda, it should be less than or equal to the square of this multiplicity. This is a log concave. So if you look at the logs, then it satisfies a convexity property, right? Yeah, of course, Okunko proves his conjectures for the inclusion of GLK inside GLN, the top left-hand corner. So inductively for any K. But it is known that this conjecture has been shown to be false for tensor products in a paper of Chindris, Dirksen, and Wyman, composited 2007. But their examples are, in a sense, not regular, because they take mu, and when you take the tensor product and you're looking at the multiplicity of lambda, the tensor product is of the same representation. They're looking at tensor product of two representations, of the representation with itself and looking at it. It's decomposition. And they see that the convexity property, the log concavity property for the weights does not hold. So it's not clear whether the conjecture or the Okunko's conjecture on log concavity of multiplicities will hold when you work with regular weights, even in the tensor product situation. Anyway, so that's a thing. I think I stop here. Sorry, I went probably a bit fast, but I finished well ahead of time. Maybe people can enjoy it.
No, that's fine. I think people would welcome that. There is no harm in that. So let's thank Rajan for his talk before we open it to questions. we have lots of time for questions, so please unmute and ask.
Thanks. Nobody is there to test my ignorance, so it's okay.
No, I think you'll be tested later. Maybe they're.
Sorry, I'm. Yeah, it's a. Yeah, maybe I should have. I don't. Yeah.
Okay, Rajan, can I ask you, how do you prove the convexity property for SLN that you talked about, lambda plus K alpha?
Yeah. So what happens is, see, if I take lambda plus K alpha, and I would like to take, suppose if I look at J, right? So the J alpha is, you look at J or whatever it is J times lambda plus N minus J times lambda plus K alpha, lambda plus J alpha, right? You know, the usual divided by K. Sorry, K is the length of the interval. And so the convexity elements are, you look at J lambda by K, J by K times lambda plus K minus J by K into lambda plus K alpha, right? That would give one of those things, either lambda plus J alpha or lambda plus K minus J times alpha. So you would like to do that. So you can multiply, you can look at the K tensor product, and you know that you can look at the J-fold tensor product, and then you can look at the K minus J-fold tensor product. You know this eigenvalues will occur. The K lambda will occur, and N minus K times whatever that lambda plus K alpha will also occur, J minus K. And when you look at the sum, you get actually that the K multiple of this corresponding weight occurs in the thing because of the convexity. And by saturation, it will imply that that weight will also occur. The saturation and the convexity tells you that in some sense, the weights which occur are going to be rational with respect to the groups.
So for the saturation conjecture, what are the tensor, which tensor product are you looking at? V1 tensor V2 tensor adjoint representation to the kth power?
No. No. You're looking at V nu tensor V nu.
Yeah.
And you're looking at the dual of V lambda star, right? Or whatever, sitting inside. Yeah.
Okay.
Or it does not matter. You're looking at V lambda sitting inside that. Yeah. And then you'll be, so the weights, if you push to the thing, it will be nu plus nu minus W naught plus W naught lambda equal to 0.
Okay.
Because the dual, you have to work with the dual of this, right?
All right.
Yeah.
Okay. No, I get it. So the proof uses the saturation conjecture, and which direction of the saturation conjecture? That if there
if
is
it occurs in a multiple, then the saturation plus the convexity property also, right?
Okay.
The fact that all those weights, see the convexity comes, that the saturation cone, eigencone, it is not clear that it's a convex body.
But it is true by saturation, or it's true independently?
It is, I think it is true because of the moment map considerations.
I see. So, in fact, yesterday when I was giving the talk, I was a bit confused that saturation is if and only if, and one thinks about one direction to be non-obvious and whether the other direction is obvious.
Yeah, I think the other direction is obvious, but we'll talk about it. Yeah.
All right. Okay.
As I said,
Sorry.
you are exposing
Yes. Good.
The other direction should be obvious. Yes, you are saying that, but I think the other direction from going from lambda 1 tensor lambda 2 tensor lambda m invariance is non-zero to that of the multiple is, I think, is
good.
Not too difficult, I think. I think so. I remember probably Fulton's article might give, but I have not looked at Fulton. I looked at Fulton, last year, so I have not. Don't remember it immediately right
No, it is obvious, I think, from other points of view as well. So, I mean,
now. It is obvious, yeah.
Yeah, it is obvious. Yeah.
It is obvious from which point of view, Raghavan?
For example, I am thinking in terms of Littleman paths.
No, but that's not obvious. I mean, an obvious proof is which works for reductive groups.
Okay.
So an obvious
okay.
proof should not work for GLN.
Okay,
If
okay,
it's
okay.
only GLN, then it cannot be obvious.
Yeah, okay. Yeah, so see, the other thing is, somehow, see, what both Okunkov and this convexity is saying is that in some sense, when you take the limits, like you look at all the multiples n lambda, n mu and whatnot, then there are some nice descriptions which is allowed. Or Okunkov says, like you look at the limit of the unitary group as n goes to infinity, then some things looks nice. But the point is to, I don't know, to work with, you fix a nu and look at its tensor product and look at the weights which are occurring there. Now, how nice are those weights? Do they form some kind of convex body? If so, yes, it seems to be with respect to the root lattice that it seems to satisfy some convexity property. But then you would like to know, does it have a nice description? What are the faces? What are the corners? Is that true? And what is, for instance, alpha chain, the length of an alpha chain? All these questions seem to be there, but unfortunately, I don't have anything to say beyond this minor observation. That's it. So,
sorry, the faces of what polytope again?
If I take the tensor product and it seems to have some kind of you can look at its complex, the convex closure, right? Of the highest weights which occur in this.
Of the weights which occur in this, right? Of the support, you mean?
Of the support.
Of the tensor product, right?
Right. No, what is it? Actually, when you look at, if you look at rank 2 or whatever and look at the diagrams, they all look very nice.
Okay, so the tensor product isn't, somehow this PRV kind of thing doesn't imply the tensor product convex
yes,
is the
exactly.
same as the highest
I don't know. See, for instance, the PRVs give you some extreme points.
Right. But they're not all.
But do they give the, so that is exactly one of the questions. What are the extreme points for this?
That's right.
If it is a convex body or whatever, is it spanned by some, what are those extreme points?
Okay.
Are they spanned by the PRV components?
Right.
Or the generalized PRV?
Yes, sure.
Right?
Yeah.
So that, I don't think anybody has said, it's probably not, it doesn't seem to be true, because I'm not sure, it doesn't, but some more experimentation would be welcome.
Maybe Shravan has to be asked and he may have some more ideas. I wanted to point out one small thing. Since you mentioned about Okunkov and this conjecture, there was a very recent preprint last year. I don't think it's still been published. I just checked in MathSciNet by Jun Ho, or I forget how his name is pronounced, Jun Ha, H-U-H, at the IIS, and Carola Mejaros and some other people on logarithmic concavity of Schur and related polynomials. This is a preprint on the archive from 2019 September. And the abstract simply says, we show that normalized Schur polynomials are strongly log concave. As a consequence, we prove Okunkov's log concavity conjecture for Littlewood-Richardson coefficients in the special case of Kostka numbers. So this is
special case of
Kostka numbers. So the Kostka number counts the Young tableau of a given shape and weight and so on. Anyway, you decompose a Schur polynomial in several variables as a sum of Kostka number times a monomial.
So does it prove the log concavity of the multiplicities for the Littlewood-Richardson, for the tensor product?
I haven't read the paper. I just looked at the abstract. I had heard of the paper, but I can send you the link and maybe you can take a look at.
Okay. Yeah.
Absolutely, I'll do that.
No, of course, yeah. Yeah. Yeah, so this paper of Dirksen and Chindris or Kindris or Chindris, Dirksen and Wyman, they also disprove this Kunkov conjecture for some Koska or whatever, things like that.
Okay.
Um, and they use this QoS and other things, but yeah, but I really don't.
Yeah, that paper is cited in this preprint. Okay, I'll send it to you.
Yeah, that paper is a 2007 paper of
That's
incomplexity of these people. So, right, but as I said, the point is they are looking at the tensor product of the same representation. So that's not a regular one, because nu alpha plus nu of minus alpha is 0. So,
right.
and so it's not a regular. So, yeah, I don't know whether it's.
For your question about the support of lambda tensor mu, I can just say a few words about how I think about it. I don't know the answer, but if lambda is very large and dominant regular, so deep in the Weil chamber, and mu is small, then it's quite easy to show that the support is exactly the Weil orbit of mu translated by lambda. So that's all sitting inside the dominant chamber. And you have the convex hull of the Weil orbit of mu is pushed up so that it's translated by lambda. Now, as lambda gets smaller, what happens is that this Weil orbit of mu gets closer and closer to the origin. And at some point, it starts to hit the walls of the chamber. And so you get the intersection of the walls of the fundamental chamber with the convex hull of the Weil orbit of mu. And I don't know if it's completely saturated in that intersection, but I think it's pretty close to completely saturated.
So you mean to say
so the description you gave, Arun, also tells you that the Kostka numbers are special cases of the Littlewood Richardson.
Yes, yes.
So does this give a proof of the this kind of saturation or the convexity property?
I don't know. I would have to write it out, but it's some idea.
Yeah, it would be nice to prove it without appealing to saturation or immediate, because it seems to be available. It should be doable. With bare hands.